Good morning. I hope some of you have joined now. That others can join later. Not an issue. I hope I am audible to you. At least if I say one yes from your side or raise your hand, that is also allowed.
Yes, sir.
Monisha, Pavan, Chandrika, Prerana.
Yes, sir.
Yeah, I am audible now. Shall I continue?
Yes, sir.
Yeah, be relaxed. You will see that. I am sharing this YouTube link for you. If some of you are not able to join for the class today, they can also see. You can also see that. You can also hear or you can also go through the things. See, that is the third chapter, last chapter actually, gravitation, including central force motion were there in your syllabus, where the gravitation is mainly by the massive objects which can attract on each other. This we discussed in detail. Let's assume that the Earth, where the satellites are orbiting around the Earth in a perfect orbit or perfect manner. Here they have kept it as a road for the satellites. It may not be, this is a virtual road they can call to track between among the orbits, to track the satellites. How it has to happen, we'll see that. Just one or two slides I will repeat what we did. Gravitation and central force motions are very important issues. The motion caused by the central force, for example, here this is the gravity. Due to gravity, the moon is attracted towards the earth, and earth also attracted by moon due to the gravitational influence exerted by the moon. Moon revolves around the earth in an perfect orbit, okay, where the centrifugal force exerted by the moon must balance with the gravitational influence which is attracting towards the earth. If they balance, certainly moon must revolve around the earth in a perfect orbit. Similarly, all other planets, including the earth, are also revolving around the sun in a perfect orbit. Maybe an elliptical for the nearest orbit, nearest planets, inner planets I can call. Maybe some eccentricity will be there for the earth. But for the outer planets, Jovian and others, they are having high eccentricity. The motion is caused by this force. This force is known as the central force. Central force is an attractive force always, especially the orbits of planets or maybe moons. Moons means only for the Earth, and of course, you can call also the artificial satellites or natural satellites due to the central gravitation forces. This is an important testing of the Newtonian mechanics. In fact, it is not very clear how the science of mechanics would have developed if Earth had been covered with permanent clouds, obscuring the moon and the planets from the field of view. Only it is field of view of the physical view only. It is not of that kind. Newton's laws of motion, three laws, what we expect with central gravitational forces are still very much used in today's life, maybe like spacecraft trajectories to the other planets, what I showed in my previous slide actually. See that it is perfect orbit. Perfect orbit. Looks like an elliptical, need not be circular to a greater extent. Right side here you can see that the clouds and other things. Because of the clouds, you may lose the visibility, but still yeah, this is the basic definition I covered actually earlier. Central force, how it acts, assume that there will be a mass of m1 for a planet actually, m2 maybe a moon or maybe natural satellite or artificial satellites of that kind. M2 is attracted by m1. M1 directs towards m2 with a radial distance of r. If that is the case, planet is attracted towards the sun is also attracted towards planet moves in perfect orbit. It is not for the scale to a great extent. A central force and a particle is directed toward or maybe away from a fixed point in three dimensions and is spherically symmetric about that point. It is not circular like this, what I have shown actually. Spherical means from left to right, right to left, top to bottom, bottom to top, maybe diagonal of that kind. Usually we'll go with the spherical coordinates r, theta, and phi that is corresponding to the energy. We'll call them as that energy is spherically symmetric. Potential energy U must be is function of an r. For example, if the sun with a mass of m1 here is the source exerts an attractive central force on a planet of mass m2, that is the probe you can call. where r is the radial distance of separation between the planet and the sun to a great extent, or moon and the planet Earth. Both are valid, where r is the distance between their centers, and r cap is the unit vector pointing to, away from the sun always, or here pointing away from the earth always. If that is the case, the gravitation force which is acting is directly proportional to the product of the two masses over inversely proportional to the square of the distance times the constant is known as the universal gravitational constant. Why it is negative? Because as you are moving away from the source, the force should decrease. This is the unit vector. Corresponding to this, the gravitational potential energy is given by u of r is equal to same thing, but f of r times dr means one r gets cancelled here. Okay, this is the potential energy. Then, what is the central force? What we expect actually, if the force on a body is always towards a fixed point, is called the central force. Means, if a force fixed body, always it is fixed towards the sun, always it is fixed towards the planet. For a natural or artificial satellites, is known as the central force. Force is attracting towards center of it. For example, the gravitational force, maybe circular motion, simple harmonic motion, projectile motion, uniform accelerated motion, electrostatic force of attraction, okay, magnetostatic force of attraction. These are all the examples of an central force. Means force involves mass and acceleration put together. There is no doubt. But acceleration involves the differentiation of the velocity d v by dt. Velocity is the differentiation of the displacement. Means dx by dt, then d2x by dt square gives you the thing. d2x by dt square gives you the acceleration. Mass times acceleration gives you the force. There is a need right now to know the differentiation prior to it, since displacement, velocity, acceleration, and force are all vector quantities. You should know the vector prior to it, then the vectors are maybe their differentiation, and vector differentiation makes an important. How it acts, let's see that. Don't worry, you go through it. I discussed this with different examples earlier actually. The sun attracts the earth. This is the force which is acting. This is the centrifugal force which is acting outward always actually, and it keeps in this motion. F is equal to g times m1 m2 over r square, or potential energy is the same thing for the planets. If not, if you replace with the spring constant, for example, this is the spring with bob, it oscillates up and down of that kind. Similarly, the spring like central force is a fixed point source attached to the mass. F is equal to minus k times r k times r with cap. Our potential energy in 3 dimension is given by half kr square, spring constant. If not, this with Coulomb force, if we expect, instead of the masses, the product of these two charges over the r square, 1 over 4 pi epsilon naught is the constant value. Our potential energy is only with 1 over r. Means in all the three cases, like charges repel, opposite charges attracted to each other to a great extent. In all these cases, the force is along the direction of the line of joining these centers of the source point and the probe project. Means to say, there also we derived the angular momentum is constant in an orbital motion. Means a particle moving in a plane can also be defined by two vectors. This is r and v. The radius vector to the particle from the force of the center, and an initial velocity vector of a particle here. Given these two vectors, as long as the central force remains the only the force which is existing on the particle cannot move out of the plane defined by these two vectors. Means what is that? This orbital momentum, angular momentum, should be proportional to r cross times the velocity. If r cross v remains constant, certainly the particle or object should not move away from the central force field. The environment of a particle, which is subject to a central force, is invariant under the rotations about any axis through a fixed point at the origin. So the angular momentum of the particle is conserved. Conservation of angular momentum also follows the fact that the torque which is exerted should be equal to 0. R cross times F must be equal to 0 due to a central force. If the fixed point is chosen as origin of the coordinates, the particle therefore moves in a plane, there is no doubt, because its position vector r here R is perpendicular to the fixed direction. Means R is perpendicular to the position vector R is perpendicular to the R cross P. Means angular momentum L is equal to R cross P. Hence, central force problems are essentially of the two dimension. It is not of one dimension. What happens here? All these discussions, what we are assuming here is that the source of the central force is fixed in a position, the sun, for example, or the pivot of the spring, or the sources of the charge, what I gave in the example 3, either sun or here, or maybe the charge, are all at rest and lie at the same origin in our coordinate system. What is the source object right now is also in, if it is in motion, if it is accelerating, then it defines a non-inertial frame of reference. So Newton's second law cannot be used particularly in that source of the frame. Okay, is cannot be used in the source frame. We have to have some different top into concepts actually. If so, then proceed to tackle the more general situations. The so-called two-body problem they can call it is the two-body problem involving the two dynamical objects both moving around each other, pulling on each other through a force that lies along the line that joins their centers is known as the central force. How it has to happen? Just I am giving an example. See that if there are two objects, if they are under mutual attraction, see that complexities comes. Just see that. My God, very fantastic. If you are in a region where the source mass is much heavier than the probe mass, for example, Sun and Earth, or maybe Earth and Moon, Earth and natural artificial satellites. In such case, the source mass is too heavy to be affected by the mass. Then mass of the pull means a source mass will never attract such a fine, but it will not put to a great extent. Stay means so M1 essentially stays put in an inertial frame, and with M2 is orbiting around it. This is how it has to happen. This is the complexity side road. We'll solve simple problems, we'll solve simple situations, then we'll extend the theory and concept to the complexities. See, in this region, how the Earth is revolving around the Sun. If it is nearer, periapsis. If it is far away, apoapsis. And if it is on either side, it is called the solstice of that kind. Summer solstice, winter solstice. Okay, in fact, this is the summer solstice, winter solstice, equinox, those cases. Yeah, this I shown here. The Sun at the center. It is at equidistance if it is on the radius of the Earth. Actually, one astronomical unit they can call. This is the average distance of the Sun from the Earth, or average distance of the Earth from the Sun. Sun is taken as the reference point, almost 150 million kilometer. If it is nearer, periapsis they can call, or perihelion can, Earth's closest distance, perihelion. If it is farther away, aphelion, Earth's farthest distance. With reference to the moon, if the moon is near to the earth is called perigee. If the moon is far away from the earth is called the apogee. Apogee. With G means earth. Okay. Perihelion, aphelion. Periapsis, apoapsis for different planets. For example, an elliptical orbit. Here you can expect that any planet and the star, sun will be at one of these things. Periapsis is the nearest point. Apoapsis is the farthest point. We are at a distance of about 147 million kilometer, where the northern hemisphere is this is winter, and when 52 kilometer or 53 kilometer of that kind, it is at what very aphelion where we are far away. The Earth makes the revolution like the star. It's only an example. I am sharing this PPT for you also. At the end, see that small changes in the power of the force scaling with the distance that will lead to the significantly different kind of formulas. Assume that here F is inversely proportional to R square. This is well we are aware. Instead of R to the power of 2, if you are getting 1.9, for example, okay, that is the red pink color. You see that this is the black color is the fixed orbit. Fixed orbit. If it is pink or 1.9, while plotting, it has to trace in a different path. If not, if it is 2.1, okay, slightly more than that, it traces in different. This is the sun. This is the planet which is revolving, and the fine. You can see that this is the always nearest point. This is the farthest point of that kind. Okay, in practical classes, you may be getting some different values. With the difference in values, what will happen? You have to think of. If you're sending a satellite to any of the planets near to the red planet, or maybe to our own planet to revolve around the planet, if the values fixed are deviating from its original, certainly it may not have traced the same path. Due to this, don't worry with these equations under the part. How this goes with the eccentricity, they can call. It should be an ellipse or parabola or maybe a hyperbola or maybe a circle or of that kind. To represent this, I shown these shapes actually. See, this is the cone. If you divide exactly here, it becomes a circle. Can you see that? This becomes a square, it becomes a circle. If you tilt it, it becomes an ellipse. Still, if you tilt it, it becomes a parabola. Parabola. Still, off of that, it becomes a hyperbola. The difference between these two is that parabola means there should be some center. Hyperbola, there is no center. Means it comes at one point and goes back. Okay, the Halley comet has having such type of an parabola in nature actually. Okay, see that how they are defining. This is the shape of an ellipse. Okay, with the two focus, foci they can call. Sun may be either focus 1 or maybe focus 2. This is the radius from this post. Apoapsis. This is periapsis. Nearest point to the sun, farthest point to the sun. This is the semi. Major axis is the 2a. Semi minor axis is the 2b of that kind. And eccentricity lies between 0 to 1. And the radius vector we can expect how that radius can change. A times 1 minus alpha square. This is the eccentricity over 1 plus alpha times cos theta. When theta is equal to 0, this is 1 plus alpha. This is the maximum value. You can make this as 1 minus alpha to the 1 plus alpha. 1 plus alpha gets cancelled. A times 1 minus alpha means A minus alpha. That should be the value. This only for your understanding. Being this, we told that this is in a plane. You agreed that actually this is in a plane. At the same time, the angular momentum also conserved. That I discussed in last class actually. L is equal to arc times p with the angular momentum corresponding to the relative motion of any of the objects. If it happens, what happens? Rate of change of angular momentum with time must be equal to dr by dt cross. This is p. Should be p times r. Dr by dt cross p plus r times dp by dt. This is the velocity times the momentum plus r times the force which is acting on the object. But what happens? But v is the velocity, p is equal to mu times v is the angular momentum, linear momentum, okay, or which are parallel. Because of that, v cross p becomes 0. V cross p becomes 0. Once v cross p becomes 0, what happens to the central force? R cross F here, in this case, is equal to phi of R times R. This is also equal to 0. Means to say that if you take the differentiation, dl by dt is equal to 0, means that if you integrate this, L becomes constant. Thus, in case of the central force motion, the angular momentum is conserved both in direction and also in magnitude. This is what you want to write in the examination for the conservation of the angular momentum. About 5 marks. If you ask for more, you bring that central force also into the picture. This one, then you can go for that. Okay. Based on this, okay. Here I will also give, if it is a 2-dimension, for example, illustration of the Kepler's second law, that's also according to the Newton's law, I can call actually. The planet moves faster near to the sun. So that same area is swept out in given time at larger distance where the planet moves. See here, intention is that not to demonstrate the Kepler's law. Intention is that to show you that if it is nearer, it moves faster. If it is farther away, it moves slower. Think the green color arrow. Green color arrow indicates that if the length of the arrow is small, speed is less. The length of the arrow is quite larger, higher value. Okay, I will bring to this concept later. 1 second. Yeah. Being this, we thought of demonstrating you the Kepler's laws. There is no derivation. Okay, there is no detailed description. Only laws should be discussed. First law of Kepler, second law of Kepler, and third law of Kepler. Just let us see some preamble here. Copernicus, a great scientist, during the period 1473 to about 1543, he lived hardly about some 60 years, 60 to 70 years, 70 to 40, okay, 70 years. Told that sun is the center, means all planets are revolving with reference to the sun. Earlier to him, people thought that at least the earth-centric, means sun at the center, Mercury here, Venus, third planet Earth, then Mars, then Jupiter, then Saturn. These are the fixed stars. Of course, it has not happened so like that. What happened actually? There were three great scientists after the Kepler. Kepler is in between. Tycho Brahe, first person who gave the concept of the orbital mechanics, then the Kepler, then Newton came. Of course, what we are having in the curricula is the in the syllabus is the contribution by both Kepler as well as the Newton. What Newton's laws gave, Newton's laws of universal gravitation gave in such a way that force acting on any of the massive body is directly proportional to the product of the two masses over inversely proportional to the square of the distance. From this, Kepler's laws of planetary motion were derived universal law. Okay, here we can have that some orbital elements to fix for the Keplerian orbits, like the eccentricity, like semi-major axis, semi-minor axis, or maybe the inclination or declination, or maybe we can call it as some angular momentum. These some six angular orbital elements are there. No need to touch for you actually right now. As you go deeper, certainly you will learn in your next semester or higher studies. Two-body problem can also be solved, and including the trajectory equations. That is also not there in your syllabus, but these are the examples. These are the applications you can call. Orbital maneuvers. What happens even if you keep an artificial satellite in particular orbit, always it gets attracted by the Earth. Because of this attraction, the orbit may come closer and closer for the planet. If it happens, they will fire once again. Fire in the sense boosters they can call. They will boost it to push it to the higher orbit or desired orbit. Assume that an object is rotating at about 500 kilometer. If it comes some 50 kilometer less, it may not be in stable orbit. The satellite should be pushed to the 500 kilometer. Sometimes it gets reversed also. If you are pushing, they may push it to the instead of 500 kilometer, they may push it to 510, 520 kilometer. It will come back to the 500 kilometer again due to the gravitational influence. That is not a fixed orbit, but exactly 500 kilometer. Some few 5 kilometer to 10 kilometer variability should be there. Orbit perturbation analysis can be done in a greater extent when you take it up the course in physics at higher semesters. Okay. Chapter class. Please remember, only one slide is enough for you to read. What it says that first class is that the orbit of each planet is an ellipse. See, the orbit of each planet is an ellipse. Simple one with sun at one focus. That's true. Either of the focus you can choose, doesn't matter. All planets revolve around the sun in an elliptical manner. The orbit of each planet is an ellipse with sun at one focus. Means this is the major axis. If it is fraction, semi-major axis, it is minor axis, blue color, and sun should be one. This is the rectum. The line passing through, which is parallel to the minor axis, is called the lattice rectum, they can call. And second law, what happens? What it says, second law of Kepler only, the line joining the plane here, this plane, to the sun. See, for example, here, line joining this to the sun swipes equal areas in equal times. For example, the area which is swept while moving from A to B to the sun, or A to the sun, you can draw a line. This you bring this line here. This covers the entire thing. So if you are bringing here, means it has to come here. Means this area in equal amount means between C to D, or even B to sun to the C to the sun to the D, maybe E to the sun to the E to the sun to the F. This is the area. This is the equal. Assume that these are the three things. This is the center of the ellipse. This is the empty focus. Means sun is not here. Sun is at one of the focus. Planet revolves in an anticlockwise direction. The area swept between AB to sun, CD to sun, maybe EF to the sun is constant. Maybe assume that this is July of that kind. June only. This is July, July, August, September, October. This is December, January, February. Maybe in the month of February, don't take it as 28 days of that kind, or don't take it as 30 days of that kind. Equal interval of time. For example, 30 days during this period, 30 days during this period, 30 days during this period remains constant. What it says that if it is near to the sun, it moves faster. If it is far away from the sun, it moves slower, but still it covers the equal area. Area swiped by the planet in equal amount of time, interval of time must be the area, must be the constant. This is a simple one. Of course, looks like simple, but see that how that Kepler has imagined, thought of it, and gave the theory. That theory, when he gave almost during 1700, is still valid in 2022. If you want to have any modifications, kindly make it, but it should be worth of explaining the phenomena and also of the phenomena. Third law says that not it is as simple as the third law of the Newton, where third law of the Newton goes with the uh, force which action and reaction are opposite to each other, equal and opposite to each other. Here, third law says that the square of the time period is, if it completes one cycle, time period they can call the square of the time period of a planet, which is proportional to the cube of its mean distance from the sun. For example, here sun I am keeping here. Okay, the mean distance of the sun we have to estimate actually mean distance of the sun from the planet, or mean distance of the planet from the sun, how far it is actually. That is the case. If you work out this t square is proportional to the r cube. In other words, g times mass can be reduced mass you can take, or t square is equal to 4 pi square over by gm times r cube. Means the square of the period of the planet is proportional to the cube of its mean distance from the sun. Just you remember, t square is proportional to the r cube, or t is equal to r to the power of 3 by 2. There, you can't make the measurement. You can make the measurement of the r value. Otherwise, r cube is equal to t square. R cube, the same thing, constant. Means r is equal to t to the power of 2 over 3. 2 or 3. Remember up to this extent, then there is no need. Only thing is that from this slide onwards, I will explain this in detail to a greater extent for your clarification. Don't get worried or excited. Here, this classical mechanics, under the classical mechanics, we are studying this classical orbital elements, what I shown for Kepler in orbit. Earth is a sphere, fine. How they are doing that? Don't go for the further studies, but at least try to remember. This is the one is the semi-major axis, a, semi-minor axis, maybe B. Eccentricity is defined by E. Inclination by I. Is how much it is inclined from the vertical, about 45 degree, about 180 degree of that kind. This is the equatorial plane, and this blue color is the elliptical plane. If it is nearer apogee, if it is nearer perigee, if it is farther away, apogee of that kind. Okay. Argument of periapsis is that how much it is inclined with that. This omega you can call that. Okay, here this is 110 degree. From this plane, it is 110 degree. This is 110 degree. Right ascension they can call. This is with alpha, omega. This is about 50 degree. From this reference, how far it is tilted. This satellite. True anomaly. These are the things actually, but don't worry with that. These are all the things that can be used for the assessment. Here is our satellite, and if it moves here and coming, ascending node. If it is coming from down and going up, it is node called the this is ascending, this is the descending node of that kind. The orbital elements will mathematically describe an orbit in space. Means that is the position of a satellite in space they can call. These parameters are enough to define the location of a body in space for a moving object in any Keplerian orbit. This is the concept. Being this, don't worry. Semi-major axis and eccentricity, how they are linked. If they are expecting, semi-major axis is one half of the major axis, true, and is a satellite's mean distance from the primary. Means, for example, Earth. Semi-major axis describes the size of an orbit. Means it may not be exactly the same value, but at least the mean value. Eccentricity is the distance between the focus divided by the length of the semi-major axis and describes the shape of an orbit. For example, if it is a circle, that is equal to the radius, and eccentricity is 0. And if it is an ellipse, semi-major axis is greater than that value, and eccentricity lies between 0 to 1, and it should be greater than 0 and less than 1. If it is a parabola, if in certainly there is no semi-major axis, okay, and the eccentricity is 1. And if it is hyperbola, the semi-major axis is less than 0 and the eccentricity is greater than 1 of that kind. We'll see one. The same thing. Again, I'm repeating this one, how they can see that. This is if you take a shape of a cone, ice cream cone, at least you have it ice cream today or maybe day after some other time, you enjoy that. If you cut here, it becomes a circle. If you cut here, like with some tilt, ellipse. If you cut here, it becomes parabola. If you cut here by Hyperbola means go on taking the ice creams, then maybe chew at this point, you will get a hyperbola. Chew at this point, you will get a parabola. Chew at this point in ellipse. Then at the least, with only a few part of an ice cream in your hand with a cone becomes a circle. Even if you swallow it, then ice cream disappears and hyperbola first disappears, then parabola disappears, then ellipse disappears, then circle disappears, then ice cream disappears from your hand. Yeah, being this, we are having dealt with a constant called the satellites. How they are revolving? There are different orbits where the satellites can revolve around the Earth. Some classifications, they will call it as LEOs, low Earth orbit satellites. The satellites, if they are revolving between 100 to 1500 kilometer, are called the low Earth orbit satellites. For example, see that this is the pink color. Low Earth orbit satellites revolve around the Earth. Preferably, they are also in polar orbits actually. Okay. Sorry, this one. Green color. Low Earth orbits, they are not polar. Low Earth orbits, they are at yeah, parallel to the equator, low Earth orbits, between 500 kilometer to sorry, the 100 to about 1500 kilometer. Medium Earth orbits or medium range they can call between about 5000 to about 1500 kilometer they can call medium Earth. Here this is the LEOs. Medium Earth orbits are the one. Here they are also an equatorial orbits to a greater extent. Okay, LEOs are the here low Earth orbits. Okay, this is the uh, medium earth orbit here. Okay, then sorry, then geostationary orbits. Geostationary orbits are the orbits where they are stationary with reference to the earth. For example, if they send a satellite from the India, for example, for a geostationary orbit, the satellite has to always see the territory of the India, terrain of the India. It need not be fixed. It may see Pakistan, it may see Arabian Sea, it may see the Bengal, it may see the it may see the neighboring countries, Sri Lanka and others, but the area or domain is fixed. Okay, highly elliptical orbit (HEOs) they can call. See that this is the highly elliptical. Only near to that one particular point it can go highly elliptic. Okay, for all applications on Earth, like agricultural aspects, studying the oceanography, studying the terrain features, they will go with the low Earth orbits. Okay, geostationary Earth, you can see that it looks like stationary for that. Here you can see that yellow color is the one where the satellite can revolve around that. Okay, that's about 1000 kilometer. Then red color, medium, you can call it as some orbits up to about 10,000 kilometer. Green color, you can see green color, you can see that at least highly elliptical orbit. Okay, highly elliptical orbit about more than 40,000 kilometer, including geostationary they can call. This is an example. How it works, we'll see that. Pink Kepler orbit. This is for ellipse. This one focus. This is the planet, yellow color, and blue color is for the sun. V is less than the VC. The critical velocity is that. If it is a circle, the second one. If it is an ellipse, still higher one. If it is in parabola, pink color. If it is in hyperbola, the same thing. The expression also here they are given. Maybe some numerical problems you can work out or maybe think it out. Kepler's equation and time of flight will come into the picture. That also depends on the eccentricity anomaly they can call and mean anomaly they can call. If there is no anomaly, certainly satellite should be put in the same thing. Okay. Yeah. These physical laws, we'll go with the three laws in detail. Okay. Law of ellipse is known as the first law. Means all our satellites or planets revolve around the fixed mass in an elliptical orbit. It is also known as the law of ellipses. The orbit of the planets are ellipses with sun at one of the focus. Fine. Or the orbits of a satellite around this Earth are ellipses with the Earth as one of the focus. Either sun as the reference for the planet or Earth as the reference for the natural and artificial satellites. Both. This law is known as the law of ellipses. How it works? Physical laws. Is this orbit possible? No, difficult. You can't move like that. Okay, should be like this or moving here and there. You can't expect of that kind. Second law says that the line joining the planet to the center of the sun sweeps out equal area in equal amount of time. For example, let us choose the time periodicity is T1 constant, T2 is constant, T3 is constant, T4 is constant, T5 is constant, T6 is constant. Okay, means the time duration for T1, T2, T3, for example, for every month, assume that. If that is the case, the area swept for A1, area swept for A2, A3, A4, A5, A6 remains constant. If area remains constant, time duration remains constant, only the speed matters. Here, it moves faster during T6, relatively slower during T5, relatively still lower during T4, maybe too much slower during T1. Means it has to travel along, slowly it crosses. See that this is a long area it has to cover. Okay, the same thing. This is the second law. How they can give? Kepler finds satellites travel at the same speed actually here. If it is a circular, if it is a non-circular, certainly the earlier diagram, what I have shown here is the same case. Means area swept. See that T1 minus T2, T1 minus T naught must be equal to T3 minus T2. Area which is swept for 1 must be equal to area of T2. This is the example. Satellites travel at varying speeds if they are in elliptical orbit. Third law, what it says that it is also known as the law of harmonics. Okay, like circular, this one, all of them are appearing the same thing for the cylindrical. This says that squares of the periods of two orbits, squares of the periods of the two orbits of a planet is proportional to each other as the cubes of their semi-major axis. T1 square by T2 square, it must be equal to A1 cube by A2 cube, or T1 square is proportional to the A1 cube. T is proportional to A cube of that kind. How it works, we'll see that. Orbits with the same semi-major axis will have the same period. It will not happen if T1 remains constant, then certainly the T1 is having a A1 value. If T1 and T2 are same, certainly A1 and A2 are having the same values. Yeah, how that first law can be achieved? See that every body, in fact, from the Kepler's law, Newton's laws were derived as the law of inertia. Every body continues in state of uniform motion unless it is acted upon or compelled to change its state by a force imposed upon it. Second law says that the change in the momentum is proportional to the direction of the applied force. Momentum equals mass times velocity. Means our change in momentum is given by change in momentum gives the force. That force is equal to mass times acceleration as the second law. If we are not applying any of the force, it remains constant. The third law, action and reaction are equal. For every action, there is an equal and opposite reaction. Hint is the conservation of the momentum. What? Injection of requirement, for example, like a speed. If you want something to stay in an orbit, for example, okay, it has to be going very fast. If you reduce the speed, it will fall down. If you increase the speed, it may go out. Okay, you see that here. If it rotates, it has to rotate the same thing. See here, this is about 5 meter, this is about 8 kilometer. Means for every 8 kilometer, if you change the distance about by 5 meter, the speed will change. A satellite must go about almost to 28,160 kilometer per hour. 60 means kilometer per hour, or about 28,000 kilometer per hour, or about 7.8 kilometer per second to stay in the low Earth orbit satellites. Low Earth orbit, if it gives, otherwise for every 100 mile, even if it moves 5 centimeter below, it may not be the actual value. Are you moving faster or slower? The higher your altitude. Means are you moving or slower here? If you are moving in black, if you are moving in higher altitude. If it is then what we can call geostationary, the speed of geostationary satellite must be synchronized with the speed of the Earth. See that since the Earth rotates from west to east, you want to launch a satellite towards the east. Okay, This gives you about 915 miles per hour speed boost by launching towards the east. For example, like Kennedy Space Center, location in Florida, or Sriharikota from India. They will launch towards the east. It is also moving towards the east. It launch. What happens if you launch towards west or south? You have to encounter different forces and you have to give more thrust. See how the earth revolves around the sun. This is the area structure. First law, second law, then t square must be proportional to a cube is the third law. A area of A and area of B shown in the diagram are constant. What do you expect? Yeah. This is the Newton showed that the relative motion of the two spherically symmetric bodies resulting from their mutual gravitational attraction is described by the simple conic sections. Ellipses for bound orbits, bound and unbound they can call ellipses for bound orbits, okay, and parabolas and hyperbolas for unbound. This is the fixed bound object. This is the parabola, and these are the hyperbola. Difference between hyperbola and parabola is just observe that this is only one portion of the cone. This is it is cutting the cone actually. In fact, you can have the two halves. It is not more or less two halves of that kind. It is not of that kind actually. Either here or here, the same place. However, the introduction of an additional gravitating bodies produces a rich variety of the dynamical phenomena even through the basic interactions between the pairs of objects. Yeah. And this is how satellites, sorry, or maybe planets which are revolving around the sun. It is not simple orbit what we are drawing on 2 dimension. See that this is Earth is somewhere here. Okay. Maybe the shape of ellipse, circular, elliptical. This is the circular, elliptical, maybe parabolic, hyperbolic of that kind. See that this is one. Okay, periapsis, apoapsis, still circular, maybe parabola. This is parabola, still if you go hyperbola. This here, the concept of space and time can come. The mass changes the space-time variabilities, space-time variabilities. Can you see in the background the person, Einstein, who gave Newton, who gave that concept of that kind. Newton's laws of motion and gravity plays a very important role. This I discussed. I'm giving this for your information as a repetitivity. Isaac Newton developed the first physical model that explained the motion of an object on Earth and also in heavens using a single, simplified, and unified theory. Newton's theory includes 4 laws. 3 explain the motion, first law of motion, second law of motion, Newton's laws of motion, third law of motion, and the fourth one is the gravitational force. Okay, fourth law is also there. That fourth, they may not call it as a fourth law. He is having 4 laws they can call. Newton first law concerns with the inertia, means a body either remains at rest or maybe uniform motion unless it is compelled to act upon it. Consider a body of mass m1, for example, which is located at r1 with a velocity, instantaneous velocity should be rate of change of the displacement by time. And hence, the momentum will also change as the product of the mass times mass of an object to that of the velocity acquired during displacement. The acceleration produced by the net force, which is acting on that body, is given by the Newton's second law of motion. Rate of change of this momentum mass times velocity gives you the force which is acting on, or the force which is acted on that will gives you a momentum thrust they can call, because of that object moves with acceleration, that is mass times velocity. Newton's third law here states that for every action there is an equal and opposite reaction of that kind. Thus, the force on each object of a pair due to the other object is equal in magnitude. That is F12 must be equal to F21. Negative sign is mainly because it is attractive. Okay. Or you can also have the universal gravitation law, that is directly proportional to the product of the two masses over the inversely proportional to the square of the distance. Because of this, Kepler's laws were originally deduced from the careful observations of the planetary motion. They were subsequently shown to be derivable from the Newton's laws of motion together with the universal universal law of gravity. As a cartoon, just see that for your curiosity. Kepler's laws on planetary motions, how it works. The people think it of, cosmology marches on. The person who is on the left, way back, this is the person, a scientist who is sitting in the laboratory. What he says that, where the hell did it all come from? This is the dust particle. He is grooming dust particle of any kind. Every day you will groom your house, you will keep your room clean. I hope actually your hostel very clean, your campus or premises very clean. Okay, by the supporting staff to avoid the dust. Nobody likes the dust coming from the universe. Here is so where the hell did it all come from? Dust in the sense in the data when he receives the data and he receives the information either from telescope or something like that. What are all these dust particles which are interfering? How he is thinking? Kepler's first law, all planets move in an elliptical orbit with Sun at one of the focus. Fine. A circular orbit is a special case of an elliptical orbit with eccentricity 0. Here can be shown in such a way that, and was also by the Newton, will be a direct result of the inverse square of the natures of the gravitational force. Comes out to be Newton's second law plus Newton's gravitational law plus calculus as the first. Means if it is an elliptical, it is known as the bound object. If it is a circular, it is known as the unbound object. A bound object repeatedly orbits the center. That is, an unbound object need not be either eccentricity with equal to 1 or maybe greater than 1, as the case of either parabola or hyperbolas. For example, here, see this is the one. Mercury eccentricity is 0.21. Okay. This is the B is for the Halley comet. Pluto eccentricity is about 0.25. Still the farthest dwarf planet. Okay, but it is not classified as the planet after 2006. Halley comet orbit has high eccentricity about 0.97. See that Halley comet is here and Sun is here. Okay, highly eccentric. Remember that nothing physical is located at the second focus here. Even though it is Sun is here, nothing should be there here actually. Nothing is there, still traverse. The small dot, second focus or the small dot. How that Kepler's law can go? Second law can be shown by the, and was also by the Newton, to be a direct result of the fact that Newton's gravitational law gives conservation of angular momentum for each planet. Means angular momentum gets conserved. The gravitational force produces the no torque. That is, it is even though it is perpendicular to the motion, so that the angular momentum is conserved. L is equal to R cross B. Sorry, this is something has modified, and R m times mass times the R cross V should be constant. This is an example how it has to go. The radius vector from the Sun to the any of the planet sweeps equal areas in equal amount of time. Let us see the third law. Third law, what it says that the square of the orbital period of any of the planet is proportional to the cube of semi-major axis of an elliptical orbit. If the orbit is a circular, radius is r, then it follows the Newton's universal gravitation law, because the same thing, it follows. They are one and the same thing. This gravitational force supplies a centrifugal force for the users to validate in the Newton's laws. What happens? G times mass of Sun to the mass of planet over R square must be equal to mass of planet times V square by R. Centrifugal acceleration becomes mass of planet gets cancelled. And also we know that V is equal to 2 pi R over T. Then what happens if you substitute here? V is equal to 2 square, means that is 4 pi square R square over T square. Then you bring this T square left side, 4 pi square G over gravitational force, universal gravitational constant with the mass of the Sun, 4 times R cube is equal to T square R. Within the bracket, whatever it is there, if you take it as a constant as Ks, which is the same for all planets, either for here in earlier slide, I will show you, for Mercury or for Pluto or for Neptune, it is same. Means by this way, you can expect that can be shown that this is also applies to an elliptical orbit with the by replacing the R with the A, where A is the semi-major axis. Instead of R, if you replace this with A, it is valid. Ks depend upon the planet's mass. If it is not valid, if it is a valid, see if you are concentrating the movement of the planets with Sun, take the mass of the Sun. If you are working with the planet and the natural satellites or artificial satellites, for example, Earth. Actually, if we take, let us choose for the planet satellites which are revolving around the Earth. Then the mass should be, instead of mass of the Sun, mass of the Earth should be considered. Mass of the Earth should be considered. There is only one case actually. For example, Mercury, Venus, Earth, and so many, along with Moon and Sun is also there. The masses they have shown here, their mean distance they have shown here, period of revolution they have done. If you take the mean distance from the Sun, mean distance from the Sun actually, how much they are? This is the radius actually, mean radius. Huh? Okay. If you take t square by r cube from the third law, t square by r cube becomes 2.97 into 10 to the power of minus 19 for Mercury. For Venus, second planet, same. For third planet, Earth, same. For fourth planet, same. Means all almost 3 into 10 to the power of minus 19 you can make, not an issue. Means the t square by r cube remains constant. If that is the case, that is why if t square by r cube remains constant, if you know the periodicity of the Earth and you can estimate the periodicity of the rest of the planet, or if you know the periodicity of the Venus, you can estimate that how far it is from the Sun. If you know the periodicity of means when how far it can repeat its periodicity for the Jupiter, you can estimate the value of the R. This is a simple thing. You can also estimate weighing the Sun, how that Sun can be weighed, not by any physical balance, not by any of the single balance, simple balance of that kind, not by taking some of the mass of the some of the content of the Sun and making estimation of the density per unit volume that gives you the mass and extending it to the entire volume of that kind. How they are doing? We have weighed the Earth, no doubt. Now let us weigh the Sun also. Assume Earth and Sun are perfect uniform spheres. It's only an assumption. And Earth orbits is a perfect circle. Earth orbits a perfect circle. For the Earth, mass of the Earth is equal to 5.96 into 10 to the power of 24 kg. Sorry, this is a kg you can choose. Orbital period of the Earth is 1 year. 1 year. It may be about 3 into 10 to the power of 7 seconds. But orbital radius is about 150 million kilometer. If it is the case, orbital velocity is about 2 pi r over t with the same thing. R is here, t is here, hardly about 3 into 10 to the power of 4 millisecond, meter per second. Means almost 30 kilometer per second. Means Earth rotates around the Sun with a speed of about 30 kilometer per second. Means every second it revolves with a speed of about 30 kilometer. To go with the gravitational force between Earth and the Sun, force is equal to G times m times mass of the Sun to the mass of the Earth over r square. It is a circular orbit, no issue. Then according to the Newton's second law, what happens? Sigma F is equal to F times gravitational force, mass of the Earth times acceleration due to gravity, or mass of the Earth times the acceleration due to gravity of that kind. This becomes me becomes v square by r, what we got it here. If you equate it, G times this one, G times ms times me over r square times me this one, you will get the mass of the Sun as v square r by g. This v square by r by g. We know the value of the v. We know the value of the r. That is the distance of separation of the Earth from the Sun. Okay. We know the universal gravitational constant comes to be about 2 into 10 to the power of 30 kilogram. Roughly 2 into 10 to the power of 30 kilograms are nothing but almost 3.3 into 10 to the power of 5 mass of the Earth. If you compare the mass, almost you can keep 3 lakh 30,000 Earth to counterbalance 3 lakh 30,000 Earths in another pan to counterbalance the mass of the Sun. It is huge mass. That's why in a planetary system like Sun's planetary system, entire mass is due to the Sun. Yeah. This is the last topic, geosynchronous orbit. This they have given it for you for as a task for you to work out actually. In 1945, almost 70 years back, British journalist Arthur Clarke, who later became one of the most famous science fiction novelists of all the time, proposed that the new invention TV might be so somebody broadcast from satellites in so-called geosynchronous orbit, or literally meaning Earth synchronous orbits. Means from the outer space with a distance of about either 22,300 miles or equal to 36,000 kilometers from the Earth's surface. At this distance, what happens? The orbital period of a satellite equal to the orbital period of the Earth. Means Earth takes 24 hours to complete its rotation on its own axis. The satellite in the geostationary orbit also takes 24 hours to rotate around the sun, sorry, around the earth. Means both are synchronized. And here, dubbed unfeasibly by some and impossibly by others, he was largely ignored because of the great distances involved. See that if we are expecting here it revolves, there's the same thing. How it works? Inserting a satellite into the geosynchronous orbits, how the scientists will do. See, this is the Hoffman transfer they can call. They will rise one orbit to the upper orbit, then they will push velocity, it will go, then they will push the velocity, they will go. This orbit is known as the Hoffman transfer orbit. Means it revolves in the first orbit, they will boost it, they will go to the second orbit with higher radius, then again with the again with the higher radius, then again with the higher radius, then it will be pushed into the desired orbit of that kind. How to find the acceleration due to gravity at a distance greater than the Earth's surface, for example? The net force which is acting on the object should be equal to the gravitational force. This is the force due to the m times g. This is the force due to the universal gravitational constant and the mass product of the masses and the inversely proportional to the r square. The small mass gets cancelled. G becomes gm over r square. In the sense, the in fact acceleration due to gravity is independent of the mass of the object. In the sense, the gravitational force which is acting on satellite, either on moon or low Earth orbit satellites or medium Earth orbit satellites or geostationary satellites or the high-end satellites, it is independent of the mass of the satellite. It is directly proportional to the mass of the Earth alone and also distance of separation. Or if you extend it, the gravity which is acting on a planet by the gravitational force of the sun, if you do like that, it is independent of the mass of the planet, but it depends alone the mass of the sun and also the distance of separation of the planets with the sun. You can say that if that is the case, G you can estimate, you will get 9.8 meter per second square. Finding the tangential speed, how far it has to move, for example, gravitational force is equal to the force which is due to the attracting mg times mv square by r, m gets cancelled and velocity becomes square root of r times g. G is 9.8, you can take it as roughly about 9, doesn't matter, 3 times the square root of r, 3 times the square root of r. What normally they will do? At the surface of the earth, for example, 6,400 kilometer, the speed is 8 kilometer per second. Means an object at the surface of the earth moves at a speed of about 8 kilometer per second. The same thing, equating this equally, expression for the tangential velocity and solving for the r value, g by t square by 4 pi square, or r is equal to third cube root of g over t square. Substituting this, we'll try to find the what must be the speed of a satellite which is revolving in what must be the distance of an satellite if it is at a distance, if it is having a synchronization with this earth. Gm over t square, t if you put 1 year, okay, the same thing, seconds in a year, and the number of seconds in a year. 1 year means 365 days into 24 hours into 60 minutes into 60 seconds, and you'll get 22,300 miles above the surface of the earth, or about 36,000 kilometer from the surface of the earth. But including the radius, about 6,400 kilometer should go for about 42,600 kilometer is the distance of the geostationary satellite. You can use some small computers or calculators to plot a graph. R value you can change, T value will be known, then you can have the K should be the constant. This is the only the concept. How that works out, R cube by T square is equal to K, or R cube is equal to K times T square. If you take log on both sides, log R cube is equal to log K T square, or 3 times log times R is equal to 2 times log T plus log K log, you will get the slope. This is how that slope tells us that how they are related. This is and actually I want to say I will also share this PPT right now to with the Suhas. If there are any doubts, I am happy to answer you. Otherwise, we will see what can be done. Right now, this PPT, can it go to the Suhas? I will check. Yeah, please. Suhas, entire YouTube, you just check, it is there.
Yes, sir, it is there.
If you are having any doubts or queries, fine. One is that where is Suhas? Suhas is there or not?
Yes, sir.
Yeah, you are there. You are there. Fine. Fine. Uh, yeah, hardly 14 MB PPT. I hope it is not it. Suhas has received right now the PPT, and I will share the material one after the other along with this in another hour or two. In an hour or two, there are particular queries I am very happy to attempt. Otherwise, all the best. Do well your examinations. If you are having any doubt, you can contact me either over phone or through WhatsApp. Chandrika, Monisha, Pratyush, Suhas, Pavan, and Prerana. Is it okay?
Yes, sir.
Yes, sir.
Okay, thank you. First, kindly share the PPT now immediately, and also
Yes, sir. I have shared.
YouTube link, YouTube link. That PPT, that presentation is available always. Okay, thank you.